Welcome everyone to another video lesson. In this session, we will discover how Blaise Pascal transformed the binomial theorem into a powerful symbolic and combinatorial tool. The binomial theorem and combinatorics reflect two sides of the same mathematical idea. The binomial theorem provides algebraic expression for expanding powers, and combinatorics provides the counting meaning of those coefficients. Therefore, the binomial theorem expresses the combinatorial outcome, and combinatorics interprets the algebraic coefficients. By the end of this video, you will not only understand the notation of the binomial coefficients, but also learn how to apply them to real problems in algebra and combinatorics. So please pause the video and read through the learning objectives carefully. Blaise Pascal of 1653 developed a symbolic representation of the binomial coefficients by discovering a clear pattern or rule governing the coefficients of terms in a binomial expansion. This pattern, now known as Pascal's triangle, reveals that each coefficient corresponds to a combinatorial operation of combination. So in essence, Pascal unified algebraic structure and combinatorial reasoning. Let us now recall the formula and the symbolic notation of the combination operation. So we read this one as n choose r, and it counts the number of ways to select r objects from n distinct objects. So used in the binomial expansion of the form a plus b raised to the power n. So recall that n factorial is equal to n times n minus 1 times n minus 2 and so on and so forth up to 1 times 1. So the factorial operation multiplies all whole numbers from 1 up to n. So example context for this: how many ways can we choose 2 red balls from 5? Here, n is 5 and r is 2. Indeed, this simple symbol captures the universe of counting possibilities. In the binomial expansion problems, we use combinatorics to determine the coefficient of a term, where n represents the exponent of the binomial and r is the ordinal number of the term minus 1, which is also the exponent of b in the term factor a raised to n minus r b to the r. So for example, for the third term of the expansion, a plus b raised to the power n, so r is equal to 3 minus 1, that's equal to 2. So r is 2. So the term is n choose 2, a raised to n minus 2, b 2. So again, r is equal to 2 for the third term. So here's our first example. We are going to find the coefficient of the term involving a squared b squared in the expansion of a plus b raised to the power of 4. We have n is equal to 4. And the term involving a squared b squared has the exponent of b equal to 2, so r is equal to 2. So the ordinal number of the term, so we add 1 to r, so r plus 1 is 3. Again, r is 2, and we're looking at the third term. Alright, so step number 2, write the combinatorial formula to use. So in binomial theorem expansions, the order of object does not matter. Hence, we use the combination operation rather than permutation, and this is the formula. N choose r is equal to n factorial all over r factorial times n minus r factorial. Alright, so step number 3, substitute n and r into the formula. So 4 choose 2 is equal to 4 factorial all over 2 factorial times 4 minus 2 factorial. So step number 4, compute the rational expression with factorials. So we're going to expand 4 factorial up to 2 factorial because we have 2 factorial in the denominator. And now we cancel 2 factorial in the numerator and denominator. Remaining factors, 4 times 3 equals to 12 for the numerator. And for the denominator, we have 2. And 12 divided by 2 is equal to 6. Therefore, the coefficient is 6. So, conclude the result. Therefore, the term containing a squared b squared is 6a squared b squared. Alright, so the complete expansion of a plus b to the fourth is equal to a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. And yes, the third term of this expansion is 6a squared b squared. The coefficients 1, 4, 6, 4, 1 correspond to the fourth row of the Pascal's triangle, and the third number in that row is 6. Now for example number 2, we are going to verify Pascal's identity. So the problem here, verify Pascal's identity for n is equal to 5 and r is equal to 2. So recall, Pascal's identity states that n choose r is equal to n minus 1 choose r minus 1 plus n minus 1 choose r. So we substitute n with 5 and r with 2. So we have 5 choose 2 is equal to 4 choose 1 plus 4 choose 2. So again, the Pascal's identity means that each entry in the Pascal's triangle equals the sum of two coefficients directly above it, right? So we have n minus 1 and minus 1 here. And we're going to verify this by direct computation. So let's start with the left-hand side. So we have 5 choose 2. We write the factorial form. So we have 5 choose 2 is equal to 5 factorial over 2 factorial times 5 minus 2 factorial. And that would be 5 factorial all over 2 factorial times 3 factorial. Step number 2, expand 5 factorial up to 3 factorial, the largest factorial in the denominator. Step number 3, cancel the common 3 factorial factor. So the remaining factors in the numerator, we have 5 times 4, that's equal to 20. And the remaining factor in the denominator is 2 factorial, that's equal to 2. Again, expand and simplify 2 factorial is equal to 2. So we have 5 times 4 divided by 2 factorial. So that is just 20 divided by 2 and that's equal to 10. Now let's conclude for the value of 5 choose 2. That's equal to 10. That is for our left-hand side. Now for the right-hand side, first we write the Pascal's identity formula. And then we substitute, so we have this, 5 choose 2 is equal to 4 choose 1 plus 4 choose 2. So we're going to compute 4 choose 1 plus 4 choose 2. Step number 3, evaluate each binomial coefficient. So 4 choose 1 and 4 choose 2. Let's start with 4 choose 1. So we have 4 choose 1 is equal to 4 factorial over 1 factorial times 3 factorial. And we expand 4 factorial up to 3 factorial. So we have 4 times 3 factorial. And we cancel 3 factorial. So what remains in the numerator is 4. And what remains in the denominator is 1. 4 divided by 1 is equal to 4. So 4 choose 1 is equal to 4. And now for 4 choose 2. 4 choose 2 is equal to 4 factorial divided by 2 factorial times 2 factorial. Expand 4 factorial up to 2 factorial. So we have 4 times 3 times 2 factorial. Cancel 2 factorial. What remains in the numerator is 4 times 3. That's equal to 12. And what remains in the denominator is 2 factorial. That's equal to 2. 12 divided by 2 is equal to 6. Step number 4, add 2 results. 4 choose 1 is equal to 4. 4 choose 2 is equal to 6. 4 plus 6 is equal to 10. And since we have verified that both the left-hand side and the right-hand side is equal to 10, then the Pascal's identity holds true for n is equal to 5 and r is equal to 2. Again, here's our conclusion. Each number in the Pascal's triangle is the sum of the two numbers directly above it. That is a profound connection between algebraic structure and combinatorial reasoning. Now it's your turn. Pause the video and answer the following activity items to deepen your understanding. Apply the combination formula to determine the coefficients, or verify Pascal's identity in each item. Enjoy learning by doing,